Hi listeners, you are welcome to the continuation of our online tutorial class from your students ScoreBooster, your online tutorial provider for JAMB, WAEC, NECO and NAPTIP exam. For today's lecture, we shall be discussing the concepts of linear expansivity. I am Bangbade. Before we continue, we need to consider the learning outcome of this particular presentation, which goes thus. At the end of this presentation, listeners should be able to define linear expansivity. They should also be able to state the mathematical expression for linear expansivity. They are also expected to state the applications of linear expansivity. And lastly, they should be able to solve relevant UTME questions relating to linear expansivity. Now onto the concepts of linear expansivity. By linear expansivity, we mean the fractional increase in length per degree rise in temperature. I repeat, linear expansivity can be defined as the fractional increase in length per degree rise in temperature. Mathematically, the linear expansivity alpha equals change in length over original length times change in temperature, i.e. alpha equals LF minus Li over Li times delta theta. LF in this case represents the final length, while Li is the initial length. Delta theta represents change in temperature, which is theta 2 minus theta 1. The unit of linear expansivity is per Kelvin or per degree Celsius. Now, having understood the meaning of linear expansivity, the next thing we shall be considering is the applications of linear expansivity. And the first we shall be discussing is that linear expansivity helps in preventing collapse of breach during the marching of battalions or soldiers. Also, the application of linear expansivity helps in construction of bimetallic strip, which consists of equal lengths of two different metals with different linear expansivities. This is applied in making thermostat. Bimetallic strip is used in making thermostats and switch in pressing machines, refrigerator, electrical thermometer, fire alarm, etc. Another application of linear expansivity is balancing of wheel of clock in wristwatch. And lastly, linear expansivity also assists in easy removal of bolts and nuts. When it's very tight, after heating it, the bolt and nut will expand, and this will allow it to be removed or loosened easily. Now on to some questions from UTME, and the first question we shall be considering comes from 1982, number 22, and the question goes thus. A rod of length 10 cm is heated through 100 degrees Celsius and its final length is 10.26 cm. What is the coefficient of the linear expansivity of the rod? You have option A to be 0.026 per degree Celsius. Option B is 0.00026 per degree Celsius. Option C is 0.26 per degree Celsius. Option D is 1.0026 per degree Celsius, while option E is 1.026 per degree Celsius. Now on to the solution. The first step is to write out the given parameters, and from the question we are given the natural length L1 to be 10 centimeter. That is the original length. And we're also given the final length to be 10.26 centimeter. And the change in temperature to be 100 degrees Celsius. We have to recall that our linear expansivity alpha is given as L, that is the final length minus initial length over initial length times change in temperature. And if we substitute for that, we're going to have linear expansivity alpha equals final length, that is LF, which is 10.26 minus initial length, which is 10.0, divided by initial length, which is 10, times change in temperature, which is 100. So here now, 10.26 minus 10 will give us 0.26, divided by 10 times 100 will give us 1000, making our answer to be 0.00026 per degree Celsius, which is option B, making option B to be the correct answer for this particular presentation. Now, the next question we shall be considering comes from 1980, number 44, and the question goes thus: the ratio of the linear expansivity of copper to that of iron is approximately 1.5. A specimen of iron and a specimen of copper expand by the same amount per unit rise in temperature. The ratio of their length is dash. We have option A here to be 3, option B is 1:5, option C is 1:32, option D is 1, while option E is 0.67. Now on to the solution. We have to recall that our linear expansivity alpha is equal to change in length, which is final length minus initial length over initial length times change in temperature. And also that this final length minus initial length, that is LF minus LI, is equal to change in length. Therefore, our linear expansivity alpha equals delta L, which is change in length, over Li delta H. If we cross multiply to make delta L the subject of formula, then we will have delta L equals alpha, that is linear expansivity, times initial length, then times change in temperature. Because of the same expansion per unit rise in temperature as stated in the question, then we can equate the change in length of iron to that of copper. Therefore, if we denote the change in length of copper by alpha C times LC, while that of iron is alpha I times Li, by the time we equate it, since they share the same temperature rise, then delta theta will be cut out. So delta L will remain Li delta, it will remain Li times linear expansivity. So the delta L of copper will be equal to that of iron, and that will lead us to alpha, that is linear expansivity of copper, times initial length of copper times change in temperature will be equal to the linear expansivity of iron times initial length of iron times change in temperature. But because they said the change in temperature is the same, so we are going to cut it out, and we'll be left with the alpha C, that is linear expansivity of copper times initial length of copper, equals alpha I, linear expansivity of iron times initial length of iron. So we can collect the like times to find the ratio to make the length to be on one side and linear expansivity to be on the other side. And by dividing through by L1, we can have LC over Li equals alpha I over alpha C. I mean, eventually when we try to collect the lactans, making L to be in one side and alpha to be in the other side, that will give us the initial length of copper over linear length of iron over linear expansivity of iron over initial length of copper over initial length of iron will be equal to linear expansivity of iron over linear expansivity of copper, i.e. Fc over Li will be equal to alpha I over alpha C. And from the question we've been given that the ratio of linear expansivity of copper to that of iron is 1.5. That means iron will be equal to 1.5, linear expansivity of iron equals 1.5 times that of copper. So if we substitute that, we're going to have our LC over Li will be equal to alpha I, which is linear expansivity of iron, then over what? Over 1.5 alpha I. So, and that will give us, when we cut alpha I away, our LC over Li will be 1 over 1.5, and that is equal to 0.67, making option E the correct answer for this question. Next question we shall be considering comes from 2013, number 17, and the question goes thus. A wire of length 100.0 meter at 30 degrees Celsius has linear expansivity of 2 times 10 raised to power minus 5 per Kelvin. Calculate the length of the wire at a temperature of minus 10 degrees Celsius. Option A here is 100.08 meter, option B is 100.04 meter, option C is 99.96 meter, while option D is 99.92 meter. Now on to solution. The first step is to write out the given parameters. Then from the question, we have the initial length Li to be 100 meter. The final length is not given, and of course that is what they asked us to find. Then we are given the theta 1, which is the initial temperature, to be 30, while theta 2, which is final temperature, is minus 10 degrees Celsius. Then the change in theta will be theta 2 minus theta 1, and that will be minus 10 minus 30, giving us minus 40 degrees Celsius. Now we have to recall that our linear expansivity alpha equals final length minus initial length, final length LF minus initial length Li over initial length Li times change in temperature. So if we substitute for this, our linear expansivity alpha is 2 times 10 raised to the power minus 5 per Kelvin, which is now equal to the final length, which is unknown, minus initial length, which is 100, divided by initial length, which is 100, then times change in temperature, which is minus 10 minus 30. Then we can cross multiply to get 2 times 10 raised to the power minus 5 times 100, then times minus 10 minus 30 is minus 40. Then we now be equal to LF minus 100. So if we evaluate 2 times 10 raised to the power minus 5 times 100 times minus 40, it will give us minus 0.08, which is equal to final length LF minus 100 meter. Then we can make LF the subject by transferring 100 to the other side to get minus 0.08 meter plus 100 meter. And that will give us 99.92 meter, making option D the correct answer for this particular question. Now on to practice question. And the first question here for your practice comes from 1990, number 16. And the question goes thus. A bar of initial length L0 is heated through a temperature change of delta T to a new length L. The linear expansivity alpha of the bar is dash. Option A here is L minus L0 over L delta T. Option B is L minus L0 over L0 delta T. Option C is L naught into 1 plus delta t, while option D is L minus L naught over L into 1 plus delta t. Expected answer here is option B. Then the second question for your practice comes from 1991, number 16. And the question goes thus. A brass rod is 2 meters long at a certain temperature. What is the length of a temperature rise of 100 Kelvin if the expansivity of the brass is 1.0 times 10 to the power minus 6 per Kelvin? Option A here represents 2.0036 meter. Option B is 2.0018 meter. Option C is 2.1800 meter, while option D is 2.0360 meter. Expected answer here is option A, which is 2.0036 meter. Now our next video will be on area expansivity with sample questions and solution from UTME. I urge you to please subscribe to our YouTube channel, like and share our videos, as we promise to be providing you with more interesting lectures on subjects relating to UTME. Thank you.